All right, it's the first day of physics. Game time. Guess the number. All right, what have we got here? How many potatoes? 5. All right, that was easy. How many grapes? 83. Hey, all right. How many pennies? 247. What? Oh, man. Oh, I forgot that one there in the back. All right. Now, what? How many grains of salt? What? No, that's too many. 2,560. Whoa. That's more than I thought there were. All right. How many stars? A whole bunch? Wow. Okay. 145,000. Whoa. Is that 250? 1, 2, 3, 250 million? Man. Oh, you know what? I bet you it's right there. I think that's a galaxy. That's a galaxy. They tricked us. Alright. How many What? Oh, no way. 250 billion. Whoa! What even number is that? That's 1, 2, 3, 4, 5, 6. I can't. You know what? There's got to be a better way to do this. Well, aloha, everyone. Today, we're going to be talking about scientific notation. We use scientific notation to express really large or really small numbers. Like, for instance, how many grains of sand are there in this field behind me? How many kilograms of rock are there in the mountains behind me? And just how big is a virus anyway? Well, today we're going to learn how to express numbers in scientific notation to answer questions like that. So, let's start off by writing down a fairly large number. 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's 1 trillion. Now, if I wanted to do math with this number, it'd be a real pain because I'd have to multiply by all those zeros. I'd have a whole bunch of things running around. So it's a lot easier just to express this in scientific notation. So here's what we do. We start off by looking for the first non-zero digit in this number. So here, our first non-zero digit is this 1. We're going to copy that, 1. We will then place a decimal point. And then we will say anything that comes after that decimal point. Now, in this case, it's just a bunch of zeros, so it's not a huge deal. But in general, we want to express probably about 3 numbers after the decimal point. If there's more than that, you're really not simplifying that number anyway. So in this case, since they're all zeros, I'm just going to put a 0 here and be done with it. But if they weren't all zeros, I'd probably round to whatever this third number after the decimal point is. So 1.0. Then we always write times 10. And then we think about how many times that decimal has moved from our original number to our new number that we're writing. So remember, if you can't find the decimal, it's right here at the end. So if it starts here, it has moved 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and it ends up right here in our new number, so it has moved 12 times. So this number would be read 1.0 times 10 to the 12. Now, sometimes you're going to have units coming along with this, something like, maybe this is in meters. Well, don't worry about that just yet. Just bring along the meters for the ride. 1.0 times 10 to the 12 meters. Let's try another one. 2, 4, 7, 3, 5, 6, 0, 0, 0, 0, 0, 0, 0, 0, 0. All right, so this number, when I look at it, I'm going to say, wow, that's okay, so this is thousands, millions, billions, trillions, yeah, 247 trillion, 356 billion, is that right? So in any case, when we're doing this number and converting it into scientific notation, we're going to take it and we're going to start like we just did with the first non-zero number, that's a 2. So 2 point. Then we're going to round to about the third number after that. So it's going to be a 4, a 7, and then since this is a 5, that 3 is going to round up to a 4. So it's going to be 4, 7, 4. And then we're going to say times 10, and then we're going to say how far did the decimal move? Well, it starts back here, it ends way over here, so we're going to have to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is 2.474 times 10 to the 14th. If there was a unit on this, like, I don't know, seconds, let's say, this is 2.474 times 10 to the 14th seconds. It's pretty straightforward to put a number into scientific notation when it's big. But sometimes a number is going to be really small. What do I mean by that? Well, like that size of the virus we were talking about. Really small numbers, or maybe the size of an atom. What if you have a number like this? 0.00000000325. Okay, if we're changing this number into scientific notation, we're again going to start with the first non-zero number. The difference being that in this case, the first non-zero number is way over here. It's a 3. So it's going to be 3 point. What are the numbers after that? Well, 2, 5. Everything after that isn't shown, so it's a 0. So we're not going to show them. Times 10 to the. Okay, now here it's the decimal starts off right here between these two zeros, and it's going to end up between the 3 and the 2 right there. So that means it moves 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So the decimal moved a total of 9 times. But there's one small difference between what we just did and what we're doing now. Instead of the decimal moving to the left, the decimal is moving to the right, which means since it's going the other way, this 9 needs to have a negative sign. So here's what you want to remember. There are 3 parts to scientific notation. This part out here in the front, the 3.25, this is called the coefficient. The 10 is called the base. And this negative 9 up here is called the exponent. If a number is big, what do I mean by big? Bigger than 1, probably. Your exponent is positive. So if a number is big, the exponent is positive. And if a number is small, what do I mean by that? Between 0 and 1 maybe, or 0 and negative 1. If a number, I don't know if I could spell, is small, exponents are going to be negative. But Mr. Williamson, what if you have a really big negative number? Like you owe the bank $1 billion. Well, that's pretty straightforward. If you owed the bank $1 billion, you'd have a negative sign out in the front, sort of like this. Which means you would just take that negative sign along in the front, out front here. Negative 1.0 times 10, well, that's not a billion, it's a trillion, but you get what I mean. But what happens if we're trying to go the other way? What do I mean by that? What if we have a scientific notation number that we're asked to express in standard notation? So let's say we have something like this, 3.24 times 10 to the, I don't know, let's make it 13. What is this going to look like if we write it as a standard number? Hey, let's give this a unit too. Maybe we'll give it, I don't know, how about kilograms? How many kilograms is that if we were to write that as a normal number? Well, we're going to start off kind of undoing what we did in the previous step. It's going to start with a 3. We know that. There's also going to be a 2 and a 4. We know that the decimal is going to have to move a total of 13 times in order to get back to where it started from. So right now it's between the 3 and the 2. So we want this decimal to move 13 times. We know it's a big number because this exponent is positive. So we know we're going to have a bunch of zeros after the 3, 2, and 4. So we know we're starting here. I'm not going to draw a decimal there because that'll just confuse people when we're writing it. But we know we start here between the 3 and the 2. So there's 1 space here, 2 spaces there. We've got to go 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times. Now, if you don't see these numbers here, we just assume they're zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So you'll notice I had 2 pieces after the decimal, which or 2 places after the decimal, which means that this decimal, this number needed 13 minus 2 is 11. There should be 11 zeros here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And there are. Don't forget to bring along any units that are with this. In this case, it's kilograms. Let's try another one. Maybe you remember this number from chemistry. It was one of their favorites. 6.022 times 10 to the 23rd. Anybody remember that number? That was called Avogadro's number, the number of atoms in a mole, right? Atoms are molecules. So, what does this mean? Well, if I was to write this in standard notation, what would it look like? Well, it starts off with a 6, a 0, 2, 2, and then I've got to move my decimal 23 times. It starts between the 6 and the 0, so I can move it 3 times with the digits I have, which means I need to move it 20 more times with zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 6, 0, 2, 2, and a whole bunch of zeros after it. That is what a mole is. Actually, it's not exactly that. There's a couple of digits in there too that they don't teach you about, but close enough. Okay, what if we had a number that looked like this? Negative 2.1 times 10 to the negative third. What would that number look like if we wrote that as a normal number? Let's give it a unit too, seconds maybe. Okay, so how many seconds is this? Well, we're going to start. Negative isn't going to change anything. All that means, wonder how I had negative time, but oh well. So negative 2 and 1. But we need to be careful here because the decimal starts between the 2 and the 1, and this needs to be a small number. So my decimal needs to go, instead of to the right to make it a big number, I need to move left to make it a small number. So because of that, it's going to need to move. Well, I can move it 1 time to be in front of the 2, but then I don't have enough space here, so I need to be careful with that negative sign. So starting here, 1, 2, 3 should end up there. Decimal point there. The initial 0 here is probably a good idea. It's not strictly essential, but it's a good idea to help communicate what you're talking about and avoid misconceptions. And then over here at the end, don't forget to bring along the unit, seconds. So negative 0.0021 seconds. Should be pretty easy to go back and forth between scientific notation and standard notation. Of course, the most powerful thing you can do with scientific notation is not just put numbers into or out of it, or even express really big or really small numbers. In fact, the best thing about it is that with scientific notation, we can do mathematics. We can multiply, we can divide, and we can even raise to a power very easily in scientific notation. So, take for example, let's say you wanted to multiply 4.0 times 10 to the 8th times 2.0 times 10 to the 7th. It turns out you don't have to convert these into regular notation and then multiply. That would be a huge pain. Instead, we can do this in a very fast and efficient process if you understand how to do it. The first thing we're going to do is we're going to multiply coefficients. Multiply coefficients. So, this 4.0 here times this 2.0 there, 4 times 2 is 8. We're going to write times 10, so always the same base. And then the third thing we're going to do when we multiply is we are going to add the exponents. So, what is 8 plus 7? Well, that's 15. So this is 8 times 10 to the 15. And if you worked it out longhand by writing 4, 0, 0, 0, 0, 0, 0, 0 times 2, 0, 0, 0, 0, right, you should get that exact number. Okay, if a negative number is out front, take the negative. If you have a negative here, you would make sure you take that into account when you're doing that, right? Okay, then in order to divide. Division is pretty straightforward as well. Let's say we had 8 times 10 to the, 16th maybe, divided by 2 times 10 to the 3rd. When we do this, we're going to follow sort of the same things. Instead of multiplying coefficients, in this case, our first step is going to be divide the coefficients. Now, be careful, because unlike multiplication, division has to be done in a specific order. So it's always top divided by bottom. So what is 8 divided by 2? Well, that's 4. Then the second thing we're going to do, we're going to have the same base again. So 4 times 10. And then we are going to, well, with multiplication we added exponents. With division, you're going to subtract exponents. Now be careful again, because subtraction also order matters, so it's got to be top minus bottom. So in this case, 16 minus 3 is 13. So 4 times 10 to the 13 happens to be this one. Let's make it a little bit harder and try a little bit harder example here. Let's do, how about, let's take 9 times 10 to the 24 divided by negative 3 times 10 to the, how about 100? Let's see. What is 9 divided by negative 3? Well, that would be negative 3 times 10. What is 24 minus 100? Well, that would be a negative 76. So negative 3 times 10 to the negative 76. Finally, when we do raising to a power, here's what it's going to look like. Something like this. 2 times 10 to the 5th squared is equal to. Okay, so in this case, when we multiplied coefficients. When we divided coefficients. So when we square something, what do you suppose you do? You're going to square the number. You're going to raise the coefficient to the power. Raise coefficient to the power. So what is 2 squared? 2 squared is 4. Times 10, same base always. And our third step is we are going to multiply exponents. So 5 times 2 is going to be 10. 4 times 10 to the 10th is our answer to this one. So now we can multiply, we can divide, we can even raise to a power. Now, something you need to be careful of is sometimes when you're multiplying or dividing or raising to a power, you're going to get an answer that isn't quite proper scientific notation. For instance, let's say you had this, 2 times 10 to the 5th. Instead of squaring it, this time let's go to the 4th power. Let's make it bigger, to the 5th power. All right, so first thing we're going to do is raise the coefficient to the power. So we need to do 2 to the 5th. Well, that means to multiply 2 5 times. So 2 times 2 is 4. Times 2 again is 8. Times 2 again is 16. Times 2 again is 32. So 2 to the 5th is 32. Times 10 to the 5 times 5 is 25. Now, this might look like okay scientific notation, but there isn't something quite right. This 32 shouldn't be a 32, because remember, whenever we put a number in scientific notation, it's the first non-zero digits, a decimal point, and then any other digits. So this shouldn't be 32, this should be 3.2. So that means we moved our decimal one more time, which means this should be 3.2 times 10 to the not 25. We moved it one more time, so it's going to be 26 here. If your number was too big and you move it one more time, that exponent is going to increase. If your number was too small, so let's say you had 0.32 and you change it to 3.2, it would decrease, and we'd have 3.2 times 10 to the 24 probably. So be careful about that. Make sure that if you get 2 digits in your initial answer, or 3 digits even, or however many digits, you fix that scientific notation, change it to single digit, decimal point, the rest, and then figure out how many more times that decimal moved. The final thing that you need to know about scientific notation you've probably seen before, probably in chemistry, but we just wanted to review it really quickly to make sure you understand it. And that is going to be your metric prefixes. Now, metric prefixes are really just scientific notation in disguise. What do I mean by that? Well, you've probably seen some of these before. In this course, you're going to need to know the following metric prefixes. And let's start from, biggest and go smaller. So you're going to need to know giga. Giga is going to be a capital G, and it's really going to stand for times 10 to the 9th. You're going to need to know the prefix mega. Mega is represented by a capital M. It means times 10 to the 6. You're going to need to know kilo. Kilo is represented by a lowercase k. That means times 10 to the 3rd. Now, for some reason, nobody hardly ever uses the next few ones, but for some reason, we always teach them anyway. You're going to need to know hecto. Hecto is a capital H. It's going to be times 10 to the 2. You're going to need to know deca. deca is a capital D. It's going to be times 10 to the 1. You're going to need to know deci. I think I've seen this one a few times. Well, obviously that's a prefix on decimal. But also I've seen that a couple times on drinks, sort of like Kool-Aid powders that you mix up with a certain amount of deciliters of water. Kind of rare here in the United States, but you know, elsewhere sometimes you'll see those. Lowercase d, and that's times 10 to the negative 1. So be careful with those d's, the capital D and the lowercase d, because capital D is a positive 1, lowercase d is a negative 1. After deci, we have a very common one in terms of length, centi, lowercase c, so like centimeters, and that's times 10 to the negative 2. So it's 1/100th of a meter if you have a centimeter. After the centi, you have milli. Milli is going to be a lowercase m. Remember, capital M is pointy at the top. Lowercase m is kind of rounded. That's times 10 to the negative 3. We're going to have micro, which is represented by this kind of funky looking character. It's a Greek character, and that character is the letter mu. So mu for micro, times 10 to the negative 6. By the way, if you've never been instructed on how to write the mu for micro, here's what you do. It's a stick, it's kind of a U shape up here, and then kind of a tail like that. Sometimes you'll see people try to be fancy and put something there or something over here. I wouldn't worry about that. That's a good enough mu for me. Okay, and finally, nano is going to be a lowercase n. It is times 10 to the negative 9th. All right, you've probably seen these prefixes before, but the reason they're important is if we need to do a calculation and one of our units has a prefix like this, a lot of times we're going to have to get it out of that expression and change it into scientific notation before we can do any calculations or math with it. So, for instance, let's say somebody tells you that we have, I don't know, 5,000 kilowatts. So something is 5,000 kilowatts. Well, in order to do any sort of calculation on this, I need to recognize, first of all, that this initial letter of what looks like a unit isn't actually part of the unit. It's actually scientific notation in disguise. That K stands for kilo, which means times 10 to the third. So if we wanted to convert this into a correct usage, this would be 5,000 times 10 to the third watts. Don't forget to bring that watts along. Okay, so now because of this, we can see it's 5,000 times 10 to the third watts, but that scientific notation isn't quite right. We're going to have to fix it. So what are we going to do? We're going to say, oh, the decimal needs to end up here. Right now we can't see it, so it's got to be here, so it moves 1, 2, 3 more times. It's a big number, so we're going to add 3 to it. So this is going to be 5 times 10 to the 6 watts. We could also express that as 5 megawatts if we wanted to. Let's try another one. Let's say that somebody told you that we had 14 nanometers. Well, 14 nanometers, how much is that in meters? Well, it's going to be 14, but we need to recognize that nano is also hidden scientific notation. It means times 10 to the negative 9. So it's times 10 to the negative 9. Don't forget to bring along the meters. So this is 14 times 10 to the negative 9 meters. Again, not quite right scientific notation. So this is going to need to not be 14, but 1.4 times 10 to the, it starts off at negative 9, but we moved it one more time. It was bigger, which means we need to add 1 to this, which means it's going to be a negative 8 meters. 1.4 times 10 to the negative 8 meters. That one got a little bit weird at the end there. But don't worry too much about that. You'll figure it out as you get more practice. So that's the basics of scientific notation. Mahalo for watching, and see you next time, everyone.